Hi, hi everybody. We're about to start 4.4, but before I do that, I want to make a couple of comments about 4.3. I actually meant to add this on, but I forgot it. We learned that the only subspaces of R2 are R2 itself, a straight line to the origin, and the origin itself. Well, if you think about it, if if you have two straight lines that go to the origin, where is the intersection? Well, the intersection of those two straight lines is either going to be the origin, either it's going to be the lines like sort of are on top of each other, so the intersection will be the entire lines, or through the origin, or the intersection will be the origin itself. But you see that the intersection of these two subspaces is a subspace because the origin is the subspace. Further in R3, if you have let's say you have a line to the origin and a plane to the origin, well, again, either the line is going to be on that plane, so the intersection is just going to be the line itself, or the line will not be on the plane, and they're going to intersect at one point, and that one point will be the origin. Of course, the intersection between a line and R3 is just that line, which again is already a vector space. How about two planes that go to the origin? Well, two planes that go to the origin, they either intersect, either they're on top of each other. They obviously intersect. They're not, because they both go to the origin. So either they are exactly on top of each other, or they would intersect in a line that goes to the origin. So again, you see how the intersection of two subspaces is indeed a subspace. Anyway, I wanted to make that comment, and now it's on to 4.4. 4.4 is about a concept called spanning sets, which we're going to learn about, and linear independence, which we're also going to learn about. But we're going to start by revisiting a concept that we already have learned about that's called linear combinations. And you see down here at the bottom of our screen, the definition of a linear combination of vectors is basically when you multiply each vector by some scalar and add those all up, that's a linear combination. And this concept is going to come into this concept of linear combinations is going to play into both the idea of spanning sets and the idea of linear independence. So let's do it to it. Let's see what we got here. First, let's just do some examples of let's just do some examples here. Here we have three vectors in R3: 1, 3, 1, 0, 1, 2, and 0, 0, 1, 1, 0, negative 5. Now, V1, the first vector, is a linear combination of V2 and V3, because V1 is equal to 3 times V2 plus V2. If you don't believe me, 3 times 0 is 0, plus 1 gives me the 1. 3 times 1 is 3, plus 0 gives me the 3. 3 times 2 is 6. 6 minus 5 is 1. So you see, here's an example of a linear combination. Now, here we have 4 matrices, a part of M22. And these 4 matrices we're considering them as vectors now. And if you notice, V1, which matrix 1 we're calling a vector now, V1 is also can be expressed as a linear combination of V2, V3, and V4. That V1 is equal to V2 plus 2 times V3 minus V4, and that's how they see how it works out. So I take this guy. Let's just look at the upper right. 0, that's negative 2, positive 2 gives me 0. Here you have 2 plus 6, because 2 times 3 minus 0 gives me the 8. 2 plus 6 is 8, and so on and so forth. Now, it's not necessarily always going to be the case if I have a few vectors, I'm able to write one vector as a linear combination of the others. But this is just an example where I am able to. Anyway, moving right along, let's try finding a linear combination. So here we have the vector W, which is 1, 1, 1. Obviously, it's an R3. And we want to express W as a linear combination of the vectors here in set S, and those vectors are 1, 2, 3, 0, 1, 2, and -1, 0, 1. So let's just do a job. I guess I should ask you to pause the video and see if you can work this out on your own. Okay, end of pause. Here's what you should have gotten. So we want to express the vector 1, 1, 1 as some constant or some scalar times 1, 2, 3, plus another scalar times 0, 1, 2, plus another scalar times -1, 0, 1. We've done this sort of thing before. And that's going to give us the second line. And now if I just regroup, put all the first coordinates together, all the second components together, and all the third components together, this is what I got. And this is equal to the vector 1, 1, 1. So I'm setting each of them, I'm taking C1 minus C3, setting that equal to 1, 2C1 minus plus C2, setting that equal to 1, and 3C1 plus 2C2 plus C3, setting that also equal to 1. And we're going to use, now if we use Gauss-Jordan elimination, one of our lovely things that we enjoy so much, this is what we get. So actually this system, not only is it possible to express 1, 1, 1 as a linear combination of those three vectors, but we see from the fact that there's a zero row here, that the system is going to have infinitely many solutions. And the solutions, we could parameterize it, that we're going to call C3, we're going to call that T. That's generally the smart way to do it. And we're going to let, and now that means that, that means that C2 is going to be -1 minus 2t. Why is that? Because if this is t and I bring it over to the other side, I get -1 minus 2t. And C1 is going to be 1 plus t. Why is that? Because if that's -t and I bring it over to the other side, I have 1 plus t. Because don't forget, these are equations. And so therefore, just let t be any constant, any real number, and you're going to get some solution. So for example, if t equals 1, then that's going to make C3 is just going to be 1 because that is t. C2 is -1 minus 2t, which comes out to -3, and C1 is 1 plus t, which makes it 1 plus 1, which makes it 2. And then we have W is equal to 2v1 minus 3v2 plus v3. So pow, we're done. And if you would let t be anything else, let t be 0, let t be 5, let t be -17, whatever, let t be the square root of 57, you'll get different coefficients of these vectors, but they'll combine to be W. And that's the way it is. So you see, here's infinite ways we could do it. And let's do another example. Let's take the vector 1, -2, 2, and write that as a linear combination of the same vectors. So in other words, what I'm doing is I'm giving you the exact same problem. We're saying here's our set 1, 2, 3, 0, 1, 2, -1, 0, 1, and we did such a great job of expressing 1, 1, 1 as a linear combo of these three vectors. Let's express 1, -2, 2 also as a linear combination of those same three vectors. Well, if you do the same procedure that we did, just before in example 2, you are going to get C1 minus C. This should look familiar. C1 minus C3 equals 1. C2C1. But these are the same three equations. On the left side, it's exactly the same three equations. On the right side, just have different numbers. Now, if we do again, if we row reduce this, Gauss-Jordan elimination, or whatever we want to do, notice what happens here when I get to the bottom line of this matrix. The bottom line of this matrix is the bottom line is just going to be 0, 0, 0, 1. But that means, but if don't forget, that's an equation. That's saying 0x plus 0y plus 0z equals 1, and that's impossible. So that means no solutions. So the previous problem, there were infinite solutions. This problem, there are no solutions. So apparently, it was possible. These three vectors, I was able to linearly combine them to get the vector 1, 1, 1. But I was not able to linearly combine them to get this new vector W. So That's the way it goes. But we're going to see that that's a very significant concept. And that's actually going to get us into our next concept. And that's getting us the concept of spanning sets. Now, a spanning set, well, let's just get this concept. Let's start by looking at a very cool, almost idyllic situation where you have a set of vectors, and if I would look at all the different linear combinations, I could find a linear combination for any vector in the entire vector space V. So when that happens, we say that S spans V. Now the set so we'll say that set S is a spanning set of V, meaning that every vector in V can be written as a linear combination, which is kind of cool and awesome. Obviously, the vectors we had in those two previous examples are not spanning sets, because you see that they were able to combine to form one vector, but not the second vector. So obviously, not every vector in R3 could be spanned by them. Let's look at some simple ones. Suppose you have the set of vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, that clearly spans R3, because any vector, let's say vector U is equal to U1, U2, U3. So U is a vector. The U over here is a vector. The U2, U3, U4, they're all real numbers, and they're in R3. Well, this vector U could be written as U1 times 100, U2 times 010, and U3 times 001. And if you combine that, you get the vector we're trying to get, 1, 2, 3. And that's a very, very big. So this is actually called the standard spanning set, because it's pretty basic. And similarly, we have right here, if we have P2, which is all these second degree, then, and if we look at the set 1, x, x squared, well, that's also going to span, because if I have a polynomial, a second degree polynomial, a plus bx plus cx squared, well, I could write this as a plus b. I could write this as a times 1, b times x, c times x squared. So I use all three vectors in this thingy here. So we're good. We're awesome. So any polynomial of degree 2 or less can be written as a linear combination of these three vectors. I'm calling them vectors now. You get it? So these are called the standard spanning sets, because they're very simple and basic and obvious. But let's look at another spanning set. Let's say we have the set 1, 2, 3, 0, 1, 2, -2, 0, 1. Wait, isn't that the set we had before? Actually, it's almost the same. There's one thing that's different here. See right there, you have a -1, and that did not span everything, because we found a case where it didn't. That was impossible to express. But here, we're going to change the -2 to a -1. Let's see if that makes any difference. Oh, I'm sorry. Hold on one second. So what had been so a set of vectors that did not work was when you had a -1 over there, and we showed an example where it didn't work. Let's see what happens if we make that one little change, if that's going to affect anything. Well, let's say U is some random vector, U1, U2, U3. So the bold U is a vector. The U1, U2, U3, these are real numbers. And you want to find scalars, C1, C2, and C3, where I multiply them all. And I get, again, very similar equations to what I had before, except now what's the difference? There's a -2 over there. There used to be just a -1 over here. Now it's a -2. You can go back and check the tape. Anyway, the coefficient matrix has a non-zero determinant. So the coefficient matrix is 1, 0, -2, 2, 1, 0. So 3, 2, 1. you could either row reduce that, and you'll see you're going to get all ones. You're going to get the identity matrix, or you could just take the determinant and see that the determinant will not equal 0. And I'd like you to figure out on your own what the determinant is. Not that hard to figure out. And the other thing I want to say is that therefore this system will have a solution. In fact, we'll have one unique solution. So it won't be no solutions, it won't be infinite solutions. There'll be one exact solution. And that, my friends, is awesome. Now, what's an example of a set that does not span R3? Well, that will be that's here when I have the 1 here instead of when I have a -1 instead of a -2. That was an example of a set which does not span R3. And there we go. And now we're gonna. So it's interesting that the first set 1, 2, 3, 0, 1, 2, -2, 0, 1, and this other set 1, 2, 3, 0, 1, 2, -1, 0, 1. They look very similar. There's only one tiny difference, which is the -2 versus the -1, and yet there's a very significant difference because one of them spans the entire R3, and the other one does not. So that's just the way it is. Now, there's interesting pictures on the side. Let's just look at the pictures on the left before I get to this definition. Let's look at the pictures on the left. So this is S1, and these 3 vectors, if you notice, they're shooting all over the place. They do not line a common plane. And whereas these 3 vectors from S2 do line a common plane. And that makes sense why S2 does not span everything, because when 3 vectors are in the same plane, no matter how you combine them, they're still kind of trapped inside that plane. But if 3 vectors are not in the same plane, then you can combine ways to reach any point in the whole space. So that's what I'm trying to say. Now I just want to make a definition. What about it? So let's say, you may have, how do I say this? Very subtle. The words look very similar, but it's slightly different. You may have a vector space that spans the entire R3. It may not. But any vector space, if you just look at all the linear, if you just take a vector, not a vector space, any set of vectors, if you just churn out every single possible linear combination of them, and there's going to be infinitely many, linear combinations. But if you just expand that to exhaustion, so you're going to get some set of vectors, and that set is called the span of the original set S. So my original set S is a bunch of vectors, V1, V2, all the way up to VK, whatever K is, And the span of S is the set of all linear combinations of the vectors in S. So the span of S is all of the C1, V1, C2, V2, where C1 through CK are real numbers. And sometimes we write span of S like this, sometimes we write span of these vectors like that. But now there are times when the span of S is equal to the entire vector space, then we say that S spans the vector space. But right now we're not talking about, and we're partially talking about that. When span of S is equal to V, the entire vector space, then we say V is spanned, not spammed with an M, but spanned with an N by these vectors, or that S spans V. They're all kind of just, it's almost like we're learning different ways to conjugate the word span in linear combination sense. So now we want to show that the span of S, even though it may or may not be the entire vector space, but the span of any set, if you have any set of vectors, the span of those vectors will be of some vector space. It'll be in V itself, the entire V itself, or it'll be a subspace of V. And that's what this theorem is saying. It's actually not that hard to show that. So let's just look at the theorem. If S is equal to V1, V2, to VK, and that's a set of vectors in a vector space S, it's a finite set of vectors, then the span of S, which is all the linear combinations of these original vectors, is a subspace of S. And in fact, the span of S is the smallest subspace of V, that contains S, which kind of makes sense. And in the sense that every other subspace of V that contains S must contain span S. So, for example, we saw an example with the when they had those three vectors that are all lying on the same plane. They were, so the span of those three vectors was just that plane that they lied on. Well, there's that plane which was a subspace which contained those three lines. There's another subspace which contains those three lines, and that's the that's R3 itself. But R3 contains the plane that contained those lines. That's what we're trying to say. Anyway, that's what this is saying. Well, let's look at the proof. The proof is pretty, it makes a lot of sense. It's pretty simple. So all we have to show, again, the span is a subset. Clearly, the span is a subset of the big vector space. So we know from experience that all we have to show is that this span is closed under addition and scalar multiplication. And that's really simple, because if we have a vector u, which is part of this u and v are both part of the span. So u is c1 v1 c2 v2 dot dot dot, and v is d1 v1 d2 v2 dot dot dot. And of course the c's and the d's are all scalars. Well, if I add u plus v and then just and factor out the v, I get c1 plus d1, which is just another scalar, times v1, c2 plus v2 d2. So basically, it's a scalar times v1. So the sum of these two vectors is a scalar times v1, a scalar times v2, a scalar times vk. Well, that is a linear combination. So by definition, that's part of the span. And here the same thing. When I multiply everything by c, so now my new scalars are cc1, cc2, cck, . But again, this is by definition, it's a linear combination of the vectors v1, vk, because they're just a bunch of scalars times those vectors, and they add up together. And there you go. And as far as the fact that it's a smaller subspace, again, that's left as an exercise. So that's pretty awesome. Okay, this is the end of part 1. We're going to continue with 4.4 part 2, and it's going to start right here with linear dependence and independence. Everyone, it's been a pleasure and an honor and a thrill. And we're going to now stop the recording, and we'll see you in part 2.